budgets. We've already discussed daytime energy budgets and how 6 components make up that. In the nighttime energy budget, however, there's actually only 4 components that make up this particular portion of the energy budget. Now this figure 2.6, is the same figure that you see out of your textbook. So use this or use another one as your leisure. So the 4 components to the nighttime energy budget include long wave radiation, latent heat in the form of condensation, subsurface supply, and sensible heat transfer. So let's take a look at each individual component. The first one, long wave radiation. Now this is something we saw in the daytime energy budget. The same thing happens at night. This is the radiation of energy from the Earth into the atmosphere. So in our little figure here, it's already circled for you. Now, on cloudless nights, energy loss from long wave radiation is high. Yet on cloudy nights, energy loss is actually low due to long wave radiation from clouds returning to the Earth. So clouds actually form sort of like a barrier between the atmosphere above and the Earth below. So cloudless nights basically mean that long wave radiation has no place to get absorbed into. Yet cloudy nights, those clouds are able to absorb that radiation, that long wave radiation from the ground. So if you've ever noticed on cloudy nights, it tends to be a little bit warmer. On cloudless nights, it tends to be a little bit cooler, and that's because of that long wave radiation that's coming off of the surface of the Earth. Now, an example could be deserts. If you've never been to a desert, even a desert such as one that we have here, like the Great Basin out west, or the Sonora Desert, these are places that you can actually go to that aren't necessarily considered deserts full of sand. But these places can become extremely cold at night because they're cloudless. All that energy that gets absorbed during the day gets lost at night due to long wave radiation. So long wave radiation is a huge loss, or it can be, at night. The second component is latent heat transfer. Now we did see this again in the daytime, except in this case it's actually going to refer to condensation. So condensation over in our picture is circled. This is the supply of heat as dew forms on surface. We haven't talked about dew just yet, but you probably are aware of dew. You've seen dew outside before as you wake up in the morning, the dew on the grass. Now as air cools, water vapor is converted to liquid water, and this happens near the surface. Now because this happens, energy actually gets released. So energy gets back into the energy budget. Unlike with evaporation, evaporation actually uses the energy. When we go from water vapor to liquid water, we're actually releasing the energy. So that energy is able to go back into the nighttime energy budget. Now evaporation can occur at night if there's a local source of heat. So evaporation can happen, it just is pretty rare unless there is a source of heat around. Our third component is subsurface supply. Now the heat transferred to the soil and bedrock during the day may be released back to the surface during the evening. So this can radiate or actually be conducted into the heat directly above the surface. Remember, conduction is the direct contact of that air or the heat from particle to particle. And so what happens in this case is that that heat gets re-radiated back up, almost in the form of long wave radiation, except it actually is happening through the surface itself. So it's released back to the surface, which then eventually possibly could become the long wave radiation we've already discussed. So if you're noticing so far at nighttime, it seems to be losing a lot of the energy back into the atmosphere, back into the overall global energy budget. Now the fourth one, sensible heat transfer. This is something that we also saw in the daytime as well. So remember, the sensible heat transfer is just the basic movement of parcels of air through the area. So at nighttime, perhaps we have some cold air moving in that could reduce the temperature, whereas warm air might move in, which raises the temperature. So it all depends upon this particular parcel of air that's moving around will have the effect in this particular area in the evening. Now if we compare the two, we're going to talk a little bit about the temperature changes close to the surface. Now daytime and nighttime, a lot of things go on that are fairly similar, but again, they're pretty different. So like in both, we have the components, we have the sensible heat transfer, kind of these parcels of air moving in. We have latent heat transfer. In the daytime, it's evaporation. At night, it's condensation. So we do have these balances, these components that are pretty much the same. Now let's specifically talk about the temperature changes very close to the surface. Now in the daytime, we have the ground being warmed, and this is through conduction, the direct contact from particle to particle. Now at the surface, because there's a lot of friction, air movement is actually slow. Now this allows the temperature to rise in a lot of cases. So it gives more time because this air doesn't move fast because of friction. So the radiation from the sun plus the ground radiation is going to warm the air directly close to that surface. And eventually this warm air is going to rise due to convection. So during the day, what's happening is that the air at the ground level is becoming warm, and because it warms, it becomes less dense, and then it will rise by convection. So this is close to the surface during the day. Now at nighttime, remember we don't have that radiation coming in from the sun. And at night, the ground is actually cooled through radiation. We saw that with the long wave radiation leaving the Earth's surface. Now heat is transferred from the air to the ground directly above. And that air in contact with the ground loses the most heat due to conduction. So that ground, basically that ground air, is going to lose a lot of heat because of conduction. And again, once it loses that heat, it becomes a little bit cooler. So at temperature changes close to the surface do differ between day and night, and if you go back into the energy budgets that for each individual one, that will sort of help you determine why and what's going on at the surface.